Welcome to the Explainer. Today, we are diving into a really cool concept from differential geometry. We're going to talk about how you can do calculus not just on a flat piece of paper, but on pretty much any curved surface you can imagine. Okay, so let's get right into it. We all learn calculus on that nice, predictable grid of what's called Euclidean space, your standard graph paper world. But what happens when your world isn't flat? What if you need to analyze something moving or changing on the surface of a sphere or a donut or something even crazy? And that right there is the fundamental problem. Our trusty old XY coordinate system just falls apart on a curved surface. So what do you do? Well, mathematicians came up with an idea that is just brilliantly simple. They invented something called the coordinate patch. The idea is just this. If the whole surface is too complicated, don't try to tackle it all at once. Just look at a really small piece of it, because if that piece is small enough, it's almost flat. So a coordinate patch is basically a way of taking a small, flat region from a plane and using it as a little map for a small region on our curved surface. You can literally think of it like making a map of the Earth, right? We can't just flatten the whole globe onto one piece of paper without it getting all distorted and weird. But we can make really accurate flat maps of individual countries or even cities. In geometry, a surface is officially defined as anything that you can completely cover with a collection of these little coordinate patches. Okay, so now that we've got these patches, we finally have a way to put coordinates on our curvy world. And that's huge, because now we can start to build a whole new toolkit for calculus that belongs entirely to the surface itself, totally independent of the 3D space it might be sitting in. So let's start with the basics, velocity. A tangent vector is pretty much exactly what it sounds like. Imagine something moving along a path on the surface. It's instantaneous velocity at any moment. That's a tangent vector. It's got a direction, it's got a speed, and it's all happening right there, contained on the surface. Now, what if you stood at one single point on that surface, and you imagined every single possible direction you could go in that one instant? If you gathered up all those possible tangent vectors, what you'd get is a flat plane that just perfectly kisses the surface at that one spot. And that is the tangent plane. It's the surface's own local, flat approximation right at that point. So let's take a step back and see what we've actually done here. It's pretty amazing. We have successfully rebuilt the core pieces of calculus so they work on a curved surface. We've got our coordinates, thanks to the patches, and we've got our vectors, thanks to the tangent plane. We're ready to go. And this isn't just some clunky workaround. As the mathematician Barrett O'Neill put it, this new system is strictly comparable to the calculus we're used to. That means we can do all the stuff we did back on the flat plane. We can differentiate functions, analyze vector fields, we can even integrate the whole shebang. And get this, the new toolkit is so solid that even the heavy hitters, the really big fundamental theorems of vector calculus, still work. Stokes Theorem, for example. It's a cornerstone idea connecting what happens on a surface to what happens on its boundary. And you can prove it all over again using these new tools. The deep laws of calculus are preserved. Up until now, we've been picturing our sphere or our donut sitting comfortably inside our familiar 3D world. It's easy to visualize. But here's where things get really, really interesting. What if we just took that surrounding space away? Does the math still work? And the answer, which is kind of mind-blowing, is no. It doesn't need that 3D space at all. It turns out all we actually needed were those coordinate patches, the collection of flat maps, and the rules for how they stitch together. That whole 3D world was just a visual aid. This insight is a total game changer. The realization that the calculus works with or without the surrounding 3D space is honestly one of the most profound ideas in modern math and physics. It frees us up to think about an even bigger, more powerful concept. And that concept is called a manifold. You can think of it as the next level abstract version of a surface. It's a space of any dimension you can imagine that has this one crucial property. If you zoom in far enough at any point, it looks flat. It's defined purely by its collection of patches without needing to sit inside anything else. So, why should you care about manifolds? Why does this matter? Well, because this abstract idea turns out to be the absolute foundation for a huge chunk of modern physics. It's how we describe the universe. You see, in Einstein's general relativity, our universe, space-time, isn't a flat stage where things happen. It's described as a curved, four-dimensional manifold. And the laws of physics, the very rules of reality, are written in the language of calculus on this manifold. Gravity, in this picture, isn't a force. It's just the curvature of spacetime itself. So just think about that for a second. We started with a pretty simple problem, didn't we? How do you describe an ant crawling on an apple? And by figuring that out, by developing the elegant idea of the coordinate patch, we ended up with a mathematical framework powerful enough to describe the entire fabric of the cosmos. It's an incredible intellectual journey.